Hello, and welcome to the last video for this chapter, where we'll be talking about tautologies and contradictions. If you haven't already yet, go ahead and read through this section of the book, this relatively short section of the book, and make sure you understand the definitions and work through a couple examples. By the end of this, we'll be able to determine if a statement is a tautology or contradiction. We'll use both truth tables and laws of logic to do this. As well, we'll have a better understanding of Modus Ponens and Modus Tollens, two particular tautologies. Remember that a tautology is a compound statement which is true for all possible combinations of truth values of its component statements, and a contradiction is a compound statement that's false for all possible values of its component statements. So let's first just take a look at a couple examples of tautologies and contradictions. So here I have three compound statements built off of the component statement P. And I'm just going to go ahead and start filling this in and see what happens. Notice we have P or not P, and we have P and not P. So true, false are all our possible combinations. And then not P, just the opposite of that, false, true. And then we have P or not P. So here we have true or false, that's true. And false or true, that's true. One of them is true. And then P and not P, well, true and false, well, one of them is false, so this whole thing is false. And then P and not P, false and true, this is false as well. So what we can see here is that this column, P or not P, it's true no matter what truth value P has. So this is an example of a tautology. And this one is false for all possible values of its component statement. So this one is a contradiction. So think about the word contradiction. Contra meaning against, and diction meaning something that's said. So a contradiction is saying something against what's already been said, right? So if I say P and I say not P, well, that can't possibly be true. We can't possibly have P and not P. That's why it's always false. For P or not P, well, one of them has to be true, right? P is true or false, and not P will always have the opposite value. So P or not P will always be true because one of them will be true. Just like over here, one of them is always false, so it turns out to be false for everything. So we can not only verify that this is a tautology and a contradiction, but really understand why it's a tautology and why it's a contradiction. Let's take a look at one more example here. Let P and Q be statements. Determine if the statement not Q or P implies Q is a contradiction, tautology, or neither. So what we can do here to determine if this what this is we can just do a truth table. So here it's built off of right, our compound statement is not Q or P implies Q. That's built off of P implies Q, not Q, and then the component statements P and Q. So let's first list all the possible truth values for the component statements. True, 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 false, false, true, and false, false. And then not Q, I'll negate the Q column, false, true, false, true. So then P implies Q, well, we've done this a number of times. True, false, true, true. And now we'll take the disjunction of the not Q column and the P implies Q column. So false or true, that's true. True or false, that's true. False or true, true, true and true, true. And so what that means then is we have just shown through a truth table that this compound statement, it's true for all possible values, and so this is an example of a tautology. In the next couple slides, we'll take a look at some really important tautologies that are named. The first named tautology is Modus Ponens. What this means is the mode that affirms the hypothesis. All right, so we'll see exactly what that's meaning. Here's the statement of Modus Ponens. It says that P and P implies Q is a tautology. So it's saying that this statement is true for all possible values of its component statements. That's what Modus Ponens means. I said mode that affirms the hypothesis, so notice we have an implication here, P implies Q, and we have the hypothesis being true. And so this is saying that that will always imply Q, that no matter what, that always implies Q. It's always true. And so let's verify this using a truth table. Hopefully you're not sick of truth tables yet. True, 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 false, false, true, and false, false. P implies Q then, true, false, true, true. And then the conjunction of that column, P implies Q, with the P column. So true, true, that's true. True, false, that's false, and it's a conjunction. This is false, and this is false as well. And now lastly, we'll compute this column. So we'll take the P and P implies Q column and do an implication to Q. So true implies true. That's true. Now we have false implies false. Well, the hypothesis is false there, so this implication is true. And in all the other rows, the hypothesis is false, right? P and P implies Q is false, and so this will be true for all those situations. And so we have just shown that Modus Ponens really is. So we can prove Modus Ponens really works, that this statement is a tautology. So it's always true. So just like when we looked at P or not P and P and not P, we understood not just that they were contradictions or tautologies, but why they were. I'd like to do the same thing with this one. So for this, I think an example would be good. So I'll use this Mackinac Bridge $5 one. So if you cross the Mackinac Bridge, then you pay $5. So P is you cross the Mackinac Bridge. Then you pay $5. That is Q, is you pay $5. And so this sentence here is really saying P implies Q. And then the last sentence, you cross the Mackinac Bridge. So that's P again. So the first sentence is P implies Q. The second sentence is establishing P. And so in total, what we have here is P and P implies Q. And so think about just this written out in words. If it's true that if you cross the Mackinac Bridge, then you pay $5, and you cross the Mackinac Bridge, well, what can we conclude from that? Well, you must pay $5 then. So if this is true, we're assuming this is the case, then what follows must be the conclusion that we pay $5. And so that's really what Modus Ponens is saying. It's really just about understanding what an implication means. If we have an implication and we know the hypothesis is true, then the conclusion has to follow. That's really Modus Ponens. Our second named tautology is called Modus Tollens. So like Modus Ponens was mode that affirmed the hypothesis, right? We had P implies Q and we had P. So we affirm the hypothesis. Modus Tollens means mode that denies the conclusion. So we'll have P implies Q and the denial of the conclusion, not Q. And we'll see what follows from that. P implies Q and not Q implies not P. So this statement will always be true. It's a tautology. So in the last one, we verified that Modus Ponens worked through a truth table. In this one, we'll use the fact that we already know that Modus Ponens is a tautology, and we'll show that Modus Tollens is a tautology by rewriting it. So just like with equivalent statements, we could either use a truth table to verify two statements were equivalent, or we could rewrite one using laws of logic to make it look like the other one. That would also work. So same thing can happen here. We can rewrite it, and as long as we show it's an existing tautology or contradiction or neither, we know that the original one was. And so for this one, I want you to first remember that we can always rewrite, we have an equivalent statement to an implication. So if we have the implication P implies Q, that this is equivalent to its contrapositive. Not Q implies not P. Remember that, contrapositive and the implication are equivalent. And so what I'll do here is I'll rewrite P implies Q using its contrapositive. So first I'll just start by rewriting the entire statement. I need another parenthesis here. Not Q and P implies Q implies not P. And now I'm going to rewrite this. This is equivalent to if I just replace P implies Q with its contrapositive. So now we have not Q, that stays the same, and P implies Q, but I'm going to use the contrapositive here, so not Q implies not P. And just rewriting the rest of it implies not P. So take a second to notice what we have here. We have this implication not Q implies not P. If we think of this like our original implication, not Q would be the hypothesis, and not P would be the conclusion of that implication. And look at what we have, not Q, so we're affirming the hypothesis. Here we have the hypothesis and the implication, and what follows is the conclusion, not P. And so really, this statement that we have here, this equivalent statement, is a tautology because of modus ponens. We can apply modus ponens to the contrapositive of the implication. So that's one way to think of modus tollens, is it's really just modus ponens applied to the contrapositive. But again, we want to understand why this should be true. Why does this make sense that this should be a tautology? For this, I'll go back to this example. If you cross the Mackinac Bridge, then you pay $5. So again, you cross the Mackinac Bridge. This is P. Cross the Mackinac Bridge. You pay $5. That's Q. And so this first sentence is saying P implies Q. And then modus tollens, we would want to deny the conclusion. So we suppose this is true, and we also suppose that we did not pay $5. So we've denied the conclusion here. We don't have Q. So what can we conclude from this? So if you cross the Mackinac Bridge, then you pay $5, and we assume you didn't pay $5, well, it must be the case that you didn't cross the Mackinac Bridge. So that is, if we have P implies Q, and we have not Q, then what follows from that, what has to follow from that, is that the hypothesis must not have been satisfied, right? If it were satisfied, we would have had Q. But we don't have Q, therefore we must not have satisfied the hypothesis. We must have not P. So that's really what's going on here. It's about inferring that the hypothesis, inferring the denial of the hypothesis by assuming that the conclusion is false. And so that's modus tollens. So let's take a look at one more example. These are our two named ones. We'll take a look at one more example of a problem you might encounter in this section. So in this problem, we would just like to determine if the statement P implies not P is a tautology, contradiction, or neither. Now, when I see a statement like this or a problem like this where it's asking me to do something, I'll first just think about the statement that it's asking me to consider. P implies not P. Now, you might think that this is contradictory, right? It's saying if I have P, then I have not P. Right? So if P is true, then not P has to be true. But we can't have both P and not P, right? P and not P, that's a contradiction. So we might think P implies not P is a contradiction. So let's do some investigating. We can rewrite some things, right? Remember, in the last one we used that the contrapositive was equivalent to the implication. In this one, we'll use the disjunction definition of P implies Q, right? P implies Q is the same thing as not P or Q. With the Mackinac Bridge example, right? If it's true that if you cross the Mackinac Bridge then you pay $5, that's the same thing as saying either you don't cross the Mackinac Bridge or you pay $5. That's how you can remember this one. And so we'll use that one here. So instead of using a truth table, I'm going to try rewriting this, just doing some investigating, see if I can rewrite this and make it look like anything that I can identify as a tautology or contradiction. So P implies not P is the same thing as, so hypothesis P, conclusion not P. So not P is really Q up in here. That's going to go in for not P. So what we have here is not P or not P. So we have not P or not P, which is really just the same thing as saying not P, right? If I say I'm going to the movies or I'm going to the movies, well, it must be true that you're going to the movies then, because you just said the same thing twice with the disjunction. And so really what we showed here now is that we showed an equivalence of statements. We showed P implies not P is the same thing. It's an equivalent statement to not P. So these share the same truth value no matter what the truth value is for P. And so from that, we can conclude, since not P isn't a tautology and it's not a contradiction, that the same must be true for P implies not P, right? Not P could be either true or false, depending on if P is true or false, right? And so this is not a tautology or a contradiction, and so P implies not P is not a tautology or a contradiction. So this one is neither. So while it might have appeared like a conclusion, or while it might have appeared like a contradiction, it's actually neither. We could also do this by doing a truth table. So I'm just going to quickly go through a truth table here. We just have the one component statement P. So P, true, false, false, true. P implies not P, so true implies false. That's false. And then false implies true. That's true. And so we can actually verify the work we did above, because we can see that not P, the not P column, and the P implies not P column are, they have the same truth value, regardless of the truth value of P. And so that's, again, restating what we have above, that those two statements are equivalent. And we can see that it's not all false and it's not all true, and so it's neither a tautology nor a contradiction. Okay, that's the last video for this chapter. I have an activity for you for section 1.6, which is applications of logic, which I think should be hopefully a little bit fun and help you get a little bit deeper of an understanding of how logic is applied. All right, thanks for listening.